This is worksheet 6 of the atomic structure packet, and this is the worksheet where I admit that I actually lied about two things in this packet. So the first thing I lied about was when I told you that we can always assume the number of protons and electrons are equal, and we've learned there's an important exception to the rule called an ion that occurs when atoms interact with each other and give away and steal electrons. The other lie that I've been telling you, and I really think this is the last one, is I've been telling you that when you look at the periodic table and you see these two numbers, the smaller number is the atomic number, which is the number of protons, and then the bigger number is the mass. It's how heavy that element is. Okay, now that's almost the truth, that thing about the mass. Okay, but some of you guys kind of noticed, you're like, hey, why is it that that mass is like never a whole number and it's always a decimal? And I said, oh, we'll get to that later, don't worry about it. Well, it's now that we're talking about that. Okay, it turns out that this mass thing gets a little bit more complicated than I have revealed, because most elements have multiple different versions out there. And these different versions are called isotopes. Okay, so if I'm talking about an atom of carbon, then it is always, no matter what, going to have 6 protons. That atomic number is what makes it carbon. And as soon as you change that atomic number, it's not carbon anymore. Okay? But carbon can have slightly different versions that have different numbers of neutrons. And as long as it's got 6 protons, it's still carbon. Okay? And carbon's not the only atom like this. Okay? So if we look at hydrogen, for example, hydrogen has 3 isotopes. Okay, and there's some Bohr diagrams, so sort of think about these written down below. Okay, so hydrogen 1 is what we call the most abundant isotope. That word abundant you're going to see a lot when you talk about isotopes. That means it's the most common one. So if you went out on a search for hydrogen all over the world, you'd find tons of hydrogen 1 and just a little bit of the other 2. Okay, now why do we call it hydrogen 1? That's its mass. Okay, hydrogen 1 has a mass of 1. Okay, now remember, mass is protons plus neutrons. So the reason it has a mass of 1 is because it's got 1 proton and it's got, big empty space, 0 neutrons. So 1 plus 0 is 1. Okay, now that's the most common hydrogen. That's the hydrogen we normally think about when we talk about hydrogen. But it turns out in very, very small quantities, so this is very rare, there's another version of hydrogen out there. Okay, now it's still got the same atomic number, right? Hydrogen 1 had an atomic number of protons of 1. Hydrogen 2 also has an atomic number of 1, because that's what makes it hydrogen. But it's got a mass of 2. Okay, it's a little bit heavier. Why? Well, because along with that 1 proton that hydrogen has to have, it's also got 1 neutron. So 1 plus 1 gives us the mass of 2. Okay, and even less common, and this one's actually radioactive. We'll talk more about what that means in a later unit, but it's basically not stable. Okay, so it starts to break down almost as soon as it comes into existence. We've got hydrogen 3. Okay, now hydrogen 3 still got to have to be hydrogen, atomic number of 1, but it's got a mass of 3. So this is, relatively speaking, heavy. All right, still got that 1 proton it's got to have, but it's got 2 neutrons. Now, the reason it's not stable is because it's pretty hard to pack 1 proton and 2 neutrons into a tiny, tiny little space, like hydrogen. Okay, so you start having lots of neutrons. These are usually the radioactive ones that are a little unstable. But at any rate, it exists for a short period of time, and it's hydrogen 3. Okay, so just to define this, isotopes in general are atoms of the same element, like, for example, all hydrogen, but they have different masses. Okay, hydrogen 1 has a mass of 1, hydrogen 2 has a mass of 2, hydrogen 3 has a mass of 3, and this is because they have different numbers of neutrons in their nucleus. Okay, now the number of protons, that has to stay the same, or else it's not going to be hydrogen anymore, right? Okay, so this is what makes things a little bit complicated if I were to ask you, all right, then, what's the mass of hydrogen? It's like, well, I mean, hydrogen 1, I can say has a mass of 1, and hydrogen 2 has a mass of 2, and hydrogen 3 has a mass of 3. But when I ask you, well, what's the mass of hydrogen, you kind of have to take all of them into account. Okay? And the thing is, you got to take them all into account, so you'd think, like, oh, we just find an average, right? What's the mass of hydrogen? Well, we got hydrogen 1, we got hydrogen 2, we got hydrogen 3. You guys remember learning this in math class, right? So I'm going to add those all together. Okay, so that gives me 6. And then because there's 3 of them, there's 3 things, right? Hydrogen 1, hydrogen 2, hydrogen 3. I'm going to divide by 3, and that's going to give me, oh, it must have a mass of 2. But the thing is, that would only work if there was just as much hydrogen 1 as in the world as there was hydrogen 2, as there was hydrogen 3. And I just said that's not true. For all isotopes, there's always one that's a lot more common than the others. So it's actually going to take a little bit of math calculation where we think about which ones are more common, more abundant isotopes than the others, along with their masses, and that's what we're going to learn about in the next worksheet. So for now, I just want you to start thinking about what an isotope is and how we calculate its mass, and how that kind of presents a little bit of a complication in terms of talking about what the mass of a specific element is, since there's different versions with different masses out there. And we will practice these ideas more when we get to class next.